Okay, so the presentation will be about this microsimulation model that we've been working on for the past few years. But I think to start, I would like to just give you a bit of a background on the topic. So microsimulation in itself is nothing new. The idea of using microsimulation in the social sciences, similar to the way that experiments are done in the natural sciences, in fact, dates back to work that was done already in the 50s and 60s. And the first large-scale dynamic microsimulation model in the social sciences was already developed in the late 60s and 1970s. What's also nothing new is the use of microsimulation models for population projections. And in fact, most microsimulation models within the social sciences will have some form of basic modeling of demographic processes. So there's many applications and there's many well-documented models that we can turn to, such as the Canadian LSTC model. There's the DemoSim model, which is currently used by Statistics Canada. There's the Mozart model, which is used at Statistics Norway and has been used for many years. The French Statistical Office has a Destiny model, and more recently in Germany, the Microsim model has been developed that is currently used by the Federal Statistical Office of Germany. So as you can see, several national statistical institutes have microsimulation models in their toolbox, and some of them have actually been using them for very many years. However, official population projections are still rarely computed using microsimulation methods, and the cohort-component method remains the go-to model for these cases. So what is the cohort-component method? To those who might not be familiar, it's basically a deterministic model that projects the components of population change, so fertility, mortality, and migration, at the level of cohorts. So we're looking at the level of aggregated groups of individuals in the population, and we use event rates. So why is this method so popular within official statistics? It's fairly simple computationally. It does not require a broad range of input data, and it is well established in the literature. However, the cohort-component method cannot account for complex and dynamic demographic or other processes. It cannot model interactions between individuals, and it cannot produce results for a variety of characteristics at the individual level, because the problem is once we start adding more and more variables into the model, we have to split these groups more and more, and the model basically becomes intractable quite quickly. So how can we overcome some of these limitations in moving to a microsimulation for population projections? So in the microsimulation, we move to the level of individuals and we try to simulate individual life courses over time. So we're building on the characteristics of individuals rather than aggregated cohorts in the population. And we try to simulate somewhat realistic life paths, which usually goes hand in hand with including more data, more variables in the model. And this allows us to model more complex demographic processes and also individual level interactions. So how do these dynamics actually work? In the cohort-component method, we would use event rates to determine the projected paths of the components of population change. So you might have mortality rates disaggregated by age, sex, or whether someone is born domestically or foreign, or you might have some regional variable, but you wouldn't have much more than a few variables to disaggregate these rates. And what we've done in our microsimulation model is that we're converting these event rates into waiting times using the inversion method. So each person in our population, based on their individual level characteristics, will be assigned waiting times for each of the events that we're modeling. And then as we move throughout the simulation, the event with the shortest waiting time will be the one that's realized. And once an event is realized, the characteristics of this person change, the waiting times are updated. And then again, we move through the simulation until the simulated person either emigrates abroad, dies, or we reach the end of the projection horizon. So to give you a bit of a graphical simulation of these dynamics, I've just picked out 3 possible events that we could be modeling. An internal migration event, E1. A woman could be giving birth to a child, E2, and then we can have a birthday event, E3. And so if we start at the top of this graph, we can see the different waiting times. And in this case, the internal migration event, the blue line would be the shortest line, so the shortest waiting time. So once this waiting time has elapsed, the event will take place. The person will migrate to a different region, which now means that one of their characteristics has changed and the waiting times are updated. And so we move further down, we move through time, and we can see that in this case, now with these updated waiting times, the shortest waiting time would be for the birthday. So this will be the next event to take place. And so that's how we move through the simulation. I'd now like to turn to the specific implementation and what we've done in the case of Statistics Austria. So Statistics Austria for decades produced all of its population projections using the cohort-component method. And so when we implemented the microsimulation, we really wanted to make sure that we're trying to mitigate the effect of this quite fundamental change in the method that we're using. So we started by replicating the results of the cohort-component method using microsimulation, and then began to gradually sort of step-by-step extend and develop new model elements and modules. And the model that we've implemented at Statistics Austria is, of course, a dynamic model. It is case-based, and it operates in continuous time. Because of the availability of quite a lot of registered data in Austria, we're able to use administrative data for the entire Austrian population, which currently has about 9 million inhabitants. So we have 9 million rows of data to start with. But the model that we're using could in principle also be applied to a large representative sample of a population or a synthetic population. And we implement this model using ModGen, which is a microsimulation programming language, which was developed at Statistics Canada. And in our case, we're coding it in Visual Studio, which is a Microsoft product. So the first model extension that we started with, and we've actually already implemented in the Austrian population projection model, is for international emigration. So previously in the cohort-component method, we were using emigration rates. And now in place of emigration rates, we estimate piecewise constant hazards for emigration by sex and country of birth, which we've clustered into 17 country groups. And as input variables, we use age, the federal province of residence, and the duration of stay in Austria. We have chosen to start with this extension because it's fairly easy to implement. It does not require a lot of additional data. But at the same time, as you will see in the next slide, this extension is very relevant because emigration patterns can differ quite substantially based on individual level characteristics. And so what you can see in these two graphs is the example of an 18-year-old male who immigrates to Austria and lives in Vienna for two different countries of birth, or groups in the right case. So the left pane shows a person who was born in Syria, and the right pane shows a person who was born in a high-income EU member state in Northern or Western Europe, such as Denmark or Sweden. And what you see on the x-axis is the duration of stay in Austria in years. And then in both graphs, you have a blue line and a red line being the emigration hazards, the rate at which the person emigrates in a given time interval. And the blue line is the survival, so the proportion of individuals who do not emigrate until a given point in time. And so there's two things to see here. The first being the clear relationship between the duration of stay and the emigration behavior. So this is actually visible in both graphs because we can see that after the first 1 or 2 years of living in Austria, the emigration hazard starts to decline. So essentially, the people who are most likely to emigrate are the recent immigrants, whereas persons who have been living in Austria for a long time are less likely to emigrate. And the second thing that we're seeing is the clear relationship with the country of birth. So in the left pane, we see that the emigration hazard is quite low to begin with. So even in the first 1 or 2 years after immigration, this person is very unlikely to leave Austria. And then the hazard actually drops down to a value near 0 very quickly. Whereas in the case of someone born in Denmark, for example, the emigration hazard is very high in the first 2 years. And then it starts to slowly converge towards 0 as time goes on. So we can see that someone who immigrates to Austria and was born in Syria is likely to stay in Austria, and especially in the long run, whereas people who immigrate to Austria from those high-income EU member states, they usually come to work or study here for a year or two, and then they're quite likely to leave again. And so what these two graphs are showing is that there's individual level characteristics such as the duration of stay or the country of birth, which is already quite disaggregated in our model, which we just wouldn't be able to include in a cohort component method, and they clearly affect behavior, and you can see this also in aggregated emigration numbers. And with this, I will now pass the keyboard to my colleague, Philip.
Okay, thank you. So next point, model validation. So to check the model performance, we conducted an ex-post validation starting in the year 2012. So we took all the assumptions from the population projection from back then, except for the number of immigrants, because we want to see how our immigration module performed compared to the standard cohort model. So we took the actual immigration numbers for the years between 2013 and 2021, and we let our model run between 2013 and 2021. So let's first have a look on the projected population. So what you can see is the black line is the observed, the dashed orange line is our simulation, and the dotted blue line is the standard cohort model. And we can see that before 2015, 2016, both models give roughly the same values. There is only a small difference, but this changes after 2016. So you can see this kink in the line in 2016. So afterwards, you can see that actually our microsimulation gives much better results than the cohort model. And the difference in those patterns comes from our immigration module. So that's what we basically changed. So let's have a look on the projected immigration numbers. So again, black observed, dotted blue is cohort, and orange is microsimulation. So the years of 2015 and 2016 were the years of high immigration in Austria. So as Pauline mentioned, those who immigrate first are the most likely to emigrate again, meaning that after a period of high immigration, there would be a period of high emigration from the country. And this is what we can capture here. When we compare the microsimulation to the cohort model, you can see that the cohort model can't really capture this pattern, whereas the microsimulation can do that very well. So basically the message from this plot is that duration dependence of that immigration is crucial. Yeah, and this kind of pattern wouldn't be captured in a cohort component model. 2020, of course, was an outlier, so you can see that actually in the chart that for 2020 we are off. Yeah. So let's come to model extensions. So far, we have changed only the immigration module, but many more extensions of the model are possible. So currently, we are working on an education module. So that means that every simulated person would have an education path over the lifetime. So this is beneficial for the model itself, as it gives detail and higher precision. But on the other hand, the model output can also be used to make predictions which regions of Austria will need more schools, more teachers, or fewer teachers. And as a next step after that, we are planning to extend the model for an employment module. So first we would need to have education paths, and afterwards we can implement employment. So again, this would give more precision and detail, and other modules are likely to follow depending on the data. As Martin mentioned earlier, we have a project with cancer rates, cancer mortality. So we will be simulating who actually dies of cancer, who lives with cancer. But it is also possible to extend the model in depth, so to say. So to give an example what that means, we can introduce additional interactions between individuals. Currently, the only interaction that we have is between the mother and her child. So the mother passes on the information in which province they live. But this can be extended. So for example, the mother could give the child the information, which level of education she has. This would be crucial information for the kid's life path. Also, the mother's place of birth would be a very crucial information for the path of the kid. So this is things that we will be planning to introduce once we have the education module implemented. Another model extension that we actually already implemented is Ukraine. So in our last population forecast, 2022, we included Ukrainian refugees. So we decided to split their path into 3 steps. So in the first step, we have a period of high immigration from Ukraine and reduced immigration. We reduced immigration hazards basically on the patterns that we saw in the data from Q1 to 3 for 2022. So we had to reduce immigration hazard by about 1/3. Then the second phase, so the first phase you could basically see as a phase during the war. This phase then goes over to a second phase where we have on the one side higher return migration of Ukrainians, but on the other side also more immigration from Ukrainians in the sense of family reunification. So what we did here is, as we have mostly female refugees, we introduced a group of immigrants from Ukraine that have just switched characteristics. We switched the gender, but other than that, we give the same characteristics as the female refugees who are already in Austria. Yeah. So the return migration quotas for the second phase are in line with survey results because we didn't have administrative data. So we took a survey conducted last year to have emigration rates who will actually be going back to Ukraine. And then we have a phase 3 that is going back to normal, so to say, a period after the war that converges over a few years to a situation as it was before 2020. So what we saw is that when there is a higher community of an immigrant group in the country, there is also further immigrants coming. We have compared this with refugees from Chechnya. So if there is a community of immigrants, there will be more immigrants following. And in our model, we introduced till 2035 a gradual decrease to the levels of before the pandemic. Some drawbacks of the methods. So moving from the cohort-component method to a microsimulation represents a fundamental change in the way a population projection is computed. So it requires deeper understanding of model building, as well as more advanced statistical programming and data analysis skills. So in short, just more resources and computation capacities are necessary. Then if we want to extend the model, then we need more data, because every process we simulate is data-driven. So in the case of Ukraine, we did not have any administrative data, so we had to rely on survey data, what they are planning to do. Also, each new module requires additional assumptions for future developments. To give an example, we need to make assumptions which school will be most popular, which schools will parents choose for the kids. Then there are some issues when simulating demographic events in small regions that could be municipalities with only a couple hundred inhabitants. So when the population is small, rare events might just not occur in the simulation because there is a randomness effect at play that we wouldn't have in the deterministic cohort method. So this randomness effect plays a larger role when we have only a small population. So the effect would be that in small scale regional projections, you would get higher population uncertainty. And for this reason, we conduct our population projection on the federal provinces level, because they are large enough to avoid this kind of problem. Yeah. So to conclude, compared to the standard cohort component method, a microsimulation model can account for more complex and dynamic patterns in demographic processes. and produce results for a variety of individual level characteristics. And using data for Austria and starting with 2012 as a base year, we show that the proposed microsimulation model produces more accurate population projections than the cohort-component model. Lastly, we are flexible to implement new modules and get more complex scenarios. Thank you.
Many thanks. Sorry.
That's all.
Yeah. Many thanks.